let's see, how should we do k? Oh, since we're computing n, we can compute m next, and then we can compute b based off of n. So we don't even need that. Let's try this. Let's try to find a constant. Word with w, I think that's it. Okay. So find appropriate base and length. Let's do 1 billion digits right here, and our word width is that. Let's see. Oh, first. Let's see. So I have to do a little bit of tricky things here. I have to say when or unless null m, because m might be might not exist. So let's see. This and return the values here. What's missing part of loop? I'll delete that. Okay, so let's try it now. Okay. So b, what is b doing? Why is it a decimal? Of course it's because of square root. Now why did I say it here? nb minus 1, so my problem right now is that b is something that's way too small. It's saying it's 1.8, which is 1 and not, it's definitely not a valid base. If we round this up, I think it should maybe work as one possibility, but then we also didn't use digits in base, so we need to incorporate this digits in base right here. So unless and null m and n is greater than, let's see, n should be greater than digits when, let's see here. When digits in base, and then we have num digits, or we have answer digits, and then we have base b. Let's just see what this function does. Find. Okay, so find's the same thing, which is not right. The program is intended to be something that can compute things called hypergeometric functions on distributed machines, like supercomputers, ideally. So I want to be able to compute, let's say, 1 trillion digits of pi, for example, by distributing it across nodes of a supercomputer. And that's what this is supposed to do in short. So our max word is, oh, actually this should be 2 to the w1 plus this. L goes from 1 to 64, N is exp2w. It's going to try to find a suitable modulus for N. But we still need a base. So let's see. N and M. If M isn't found, it's just going to continue. But okay, so an M is found. We found an M. M must be less than our max word, and our base is, so let's compute our base here. Let B be one square root here. So and this should also be, let's see, M should be less than, or the following should be less than, so times N, do I have square defined? Yep, 1 minus B, which should be less than M, which is less than, so we have computed B already. When our digits in base is greater than, I'm going to take this out here. This still isn't correct, but let's just see what it outputs. Okay, so it still outputs the same thing. Maybe my find suitable modulus function should just find maximal moduli that can be represented with the number of bits that I have on my machine. So let's go up to there. Let's see. So let me go over to here and explain kind of what I'm about to do. There's a way to delete everything. Let's see, Control A, delete. Okay, good. So right now my find suitable modulus, find suitable. This takes as an argument the transform length. Instead, I want to write, or maybe not instead, but additionally I want to do find maximal moduli, which takes the machine word width. That maximizes the power of 2 in the modulus. So like I said, the modulus is m1, m2, ... with this 2 to the, I was saying q earlier up here. We want to maximize q and minimize this, but that turns into minimizing the number of wasted bits. When I say wasted bit, I described this in a previous stream. The wasted bits are when we do, let's do print suitable moduli for I can say a max waste argument. Oops, what did I do wrong? So what this is saying is that for a transform of length 2 to the 10, we waste no more than 4 bits. What I want now is to find very, very large powers of 2 here, like this 2 to the 13, the largest that we can possibly find that fits in our word length. So, let's see. Let's do it manually first, and also let me open up this. Let's do this manually first, and then let's see if we can write code to do it. So, if I do 2 to the 20, what do we get? 2 to the 30, 50, 60. Okay, so we're kind of bottoming out at 2 to the 60 with 4. Maybe let's say max waste is 10. Yeah, we get a ton more. So we want to be able to search for these. We want to be able to search for numbers that have a very small waste number, which is right here, where this is less than the total width of our machine words, and so on. So maybe I can start with 2 to the 58. So there's only one 64-bit number, 2 to the 50. What if we do 100 of these? 1,000? Yes, so these are all the sort of candidate ones. The best one is the 2 to the 59 right there. I'm going to copy this function. Let's delete all this stuff. Let's see, so we have, okay, so we're computing our moduli here. We have our max waste right here. We're going through each modulus and filtering them out. I think we actually need to modify find suitable moduli. Let's do this. Let's change find suitable moduli to map suitable moduli. This is gonna be good. Define map suitable moduli. Our function f on transform length, which is going to do everything that this function is doing, except we're now going to map a unary function across all of the moduli that it finds. So, we're going from 1 min while plus p count, so we take this count out. We don't do anything with count here. And we're pushing p onto this modulus, so we fun call our function on p. We now no longer maintain a list of moduli, so we can do away with that, and then we never actually return. Map the function f across